Hello again and welcome to my channel. Last time we looked at the definition of a field and we said a field, you can just think of scalars, which you can add, subtract, or divide. We move on to look at the notion of a vector space over a field. As usual, we are going to start by looking at the motivation for learning about vector spaces. So let's start with the motivation. So I teach and I walk into a class and I have Ama, Kofi, and Kweku in my class. And when I walked into class this morning, I said I wanted to take some data from them. And that data, I wanted to collect their age, their height, and also because they are students, they get some allowances or some stipends that supports their stay in school. So I'll collect some data about their stipend or their allowance that they receive. So concerning their age, I asked Amma, because they are at the university, Amma is 22 years, so quite young. Kofi is 21 years, and Kwekwe is 24 years. So their age, this is in years. I also asked about their heights, and I want to see in terms of whether they are same height or whether one is short, tall. So I checked with Amma, and Amma was 1.7 in meters, and Kofi was 1.6, and Kweku was 1.8 meters tall. So I collected this data, but as I mentioned, I want to see how well they are taking care of themselves in terms of their allowances or stipends they live on. So I checked with Amma, and because we are in Ghana, we earn in cedis. So Amma says she earns 1,500 cedis per month, Kofi 2,000 cedis, and Kweku 1,200 cedis. So I collected this data. What do I do with this data? And with this data, I would like to calculate their average age in the class. I also want to calculate their average height and also their average allowance. I can do this easily because of how I've collected this data, right? If I add this whole column, gives me what the total age, and I divide by 3. Similarly, this, and that will give me my average, right? So we can think of these containers. So we've stored this information about their age, about their height, and their stipends in containers which we can label with. So this is one container which describes the attributes of their age. This container describes the attributes of their height, and this container describes the attributes of their allowance. So we can have one container storing data about the age, and another container storing data about the height, and another container storing data about their allowance. So I'll call this container age, which here I have 22, 21, 24. The other container height, which we have 1.7, 1.6, 1.8, and the other container stipend, which we have 1,500, 2,000, and 1,200. Now with this container, I know that all entries on the first row consist of attributes of what? Amma? And attributes on the second row consist of attributes of Kofi, 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 and finally, attributes on the last row consist of attributes of what? Kweku. So you can think of vectors as containers that we store data or information is. So you can think of what vectors as containers for storing data. So that's one way to think about vectors. Now, what do we do with these containers? Are they just containers? We've seen that the ages of Ama, Kofi, and Kweku can be stored in containers, which we call a vector age. Now, there are some other people within the university community. We know that Kojo's age is twice that of Ama's. Abner's age is twice that of Kofi, and Kukwa's age is twice that of Kweku, which will mean that if Ama's age is 22, then Kojo's age will be 44, which is just 2 times 22. And that of, so we have that Kojo's age will be 2 times 22, and that of Abner will also be 2 times 21, which is the age of Kofi, and that of Kukwa will be 2 times 24. Now, if we simplify this, then we can write age underscore 2 as 2 times 22 is 44, 2 times 21 is 42, and 2 times 24 is 48. Now, if we look at these two containers, right, we can write one in terms of the other, right? How? We can write the ages of 2. We've seen that there is this commonality here. Each of the other ages we are finding, they are all twice. We saw there's a common 2 here. So we can write this as 2 times the original ages of Ama, that of Kofi, and that of Kweku. So you've seen that this container containing the ages of Ama, Kofi, and Kweku can be scaled by 2. So that takes us to this, that what vectors are objects that can be scaled. And these scalars that we have here are are coming from the field. Okay. So vectors are objects that can be scaled. Okay, good. Now also we've seen that we want to find the total age of Ama and Kojo as one object, Kofi and Abena as one object, and Kukwa and Kweku as one object. This measures the age of Ama, this measures the age of Kojo. So if you want to find their total age, that means if I add these two attributes, I get that. Now, if I want to find the total age of Kofi and Abena, I can add this and that. Similarly, if I want to find the total age of Kweku and Kukwa, I can add this and that, right? And we've seen that the things that we are adding are all either, so these are all first entries or second entries or third entries. So we can find a container which contains the total ages, which we can write as what? 22, 21, 24, plus 44, 42, 48. And what does this give us? It gives us what? The total ages. So 22 plus 44 just gives us what? 66. What do we have here? We have here 63. And here we have 72. So we've seen here that these objects we could what? Add. So that's our second rule. So vectors, we can add these ones. So vectors are objects that can be added. Can be added. Okay. So in this second motivation, we've seen that these containers can be scaled or they can be added. Okay, so that's our second one. Then finally, if you're a physicist or you work in geometry, right? You work with arrows. There are some arrows in space. So you can think of vectors as arrows in space. Now, these arrows in space, they can change directions, right? So when you have an arrow in one direction, this would be another arrow in a different direction. So this is reverse direction. And we say that we give positive for the original and a negative for the negative direction. So you can think of vectors as arrows in space, but not just arrows, right? Arrows that you can what? That can be added. That can be added or scaled. How? Right. If you want to add two arrows, like we saw in our previous motivation, if you want to add this arrow to that arrow, so if you call this arrow A, this arrow B, you want to find A plus B, you start with your original arrow and you want to add B to. So wherever A ends, that's where B starts. So you move this arrow parallel here. So this gets to B, and this starting from here to here just gives us the vector A plus B. And we said we can also what? Scale. So if you have your arrow A, then twice of it will just give to A. So a vector is just what? An arrow in space that we can add or scale. So you can, we've seen different ways of characterizing vectors. Let's just go over them. You've seen vectors as well, objects that you can add or scale, which we have seen here. But we've also seen vectors as objects that can be added or scaled, which we've seen here. And also we've seen vectors as what? Containers. So this is why we care about vectors. We can use them in different places, the applications all around us in data science and AI and in almost every field of science. Now let's get on with the definition of what a vector space is. Now, what is a vector space? We define a vector space over a field. So the scalars that we saw that we were scaling our vectors with come from the field that we defined previously. So a vector space over a field is first a non-empty set, right? So we need your set V to be non-empty, but with two operations. We said we can what? Add or scale vectors. Okay. So vectors can be added or they can be what? Scaled, such that some axioms hold. Now, if you add two vectors, you want to stay in that set V. So if you pick three elements U, V, W in V, and you add them, you want to stay in V. And if that property is satisfied, that's what we call the closure property. Similarly, if you have three vectors U, V, W, there are two different ways of adding them. You first add two and add a third, or you add the last two and add the first. You want them to give you the same answer. And this property is what we call the associative property. Thirdly, you want a do-nothing vector, right? So it's just stay where you are, you don't move in any direction. So do-nothing vector is what we call the identity. So when you add it to any vector, you remain the same. And we saw a vector in its reverse, right? So if a vector is going in one direction, the reverse goes in the opposite direction. So, and we said that the direction we will attribute with the negative. So if you have a vector, its reverse direction is negative, and when you add a vector to its reverse, so you move forward, wherever you end, you return, it gives you back. So we can think of it this way. So if you have your vector U this way, and so you move from your starting point, that will be U. Now, if you want to find U plus minus U, we said that minus U is same vector but in the reverse direction, right? So U plus minus U means you go U this direction, then wherever this ends, you start with your minus U. So we move our minus U here again. So you start from here, you end getting up, you apply your minus U. So you see, we started here and we've ended here. That's how come when you add a vector to this additive inverse, it means you did factor. So this is what we call the inverse, right? We call this the inverse under addition. And similarly, we want the addition to be commutative. So we want the order in which you add the vectors not to matter. So whether you do u plus v or v plus u, you want it to be the same. So this we call the commutative property. Now the set v under all these operations, we say that what v under addition is what is an abelian group or a commutative group. But those are not all the axioms. We want to scale vectors, right? You want to scale vectors. So if you have lambda in your field and you multiply it by your vector u, so you want what? Scalar multiplication. And also, we've seen that there are two operations now. You want the operation of addition and the operation of scalar multiplication to interact very nicely. So if you add before you scale, you want to be the same as what? You scaling before adding. And we call this what? The distributive property. So you want the distributive property to hold. And similarly, if you have two scalars which you add before multiplying by a vector, you want it to be the same as you were scaling before adding. So it's also the distributive property. Then if you have two scalars, you can choose to multiply the scalars first before multiplying by a vector. It should be the same as you multiplying the scalar, one scalar by the vector, second by it. And we call this the homogeneity. And finally, we saw that in a field, we always have this element 1, which we call the multiplicative or identity. You want that when you multiply this multiplicative identity by u in a vector, it should give you the same. So let's say what a units. So these are the 10 axioms that gives you the definition of a vector space. Now, when we think of vectors, there's one main example that comes in, right? What we started with in the motivation, which is what we think of vectors as what? Containers, right? Or tuples, right? So our examples also are first, we think of vectors as what? Arrays or containers, right? So recall, we saw what a field was, right? Things that you can add, scale, or divide. So we define n tuples. So we call this a set of what? N tuples. So n tuples. To be, you have an array with entries all coming from the field. Now, to define a vector space, all you need to do is define what the addition and scalar multiplication is. So how do we add two arrays? We add them entry-wise. So first entry plus second entry here, second entry plus second entry here, and the last entry plus the last entry. And how do we scale the vectors? A scalar times a vector, we want the scalar to multiply each of the entries here. Okay, so let me add here. A vector space is defined by the addition and scalar multiplication. Okay. By the addition and scalar multiplication. So given a set, you want to show that with the vector space, all you need to do is to define what addition is and what scalar multiplication is. Good. So we think of vectors as what? Containers or arrays, which is how most of us think about vectors, right? But vectors go beyond arrays, right? They could be matrices, right? You can think of vectors with what? With different attributes. So here we are looking at what? Matrices. So we let the sets max. So here, 2 here represents the number of rows we are considering, and this other 2 here represents the number of columns we are representing, right? So we define this to be what? Entries coming from your field, and define addition and scalar multiplication to be, now, if you have one array and another array, you add them what? Entry-wise. So this entry here is in the first row, first column. So you add it to the entry in the first row, first column. That gives you this. First row, second column, first row, second column. That gives you the addition. What about scalar multiplication? Scalar multiplication is defined by you multiplying each entry in your array by it. You can check that this satisfies all the 10 axioms of the vector space. But so that means what matrices are vectors. So maybe I add a note. So matrices are vectors. Okay. So vectors are not just the tuple that we learned about, right? Even in our next example, we see that vectors can even be continuous functions, right? So if you have a function from a real value function from R to R, which is continuous, then we take the set of all continuous functions from R and define addition of two continuous functions to be what? Individual additions and adding, and scalar multiplication to be this. So lambda f x is just lambda f of x. Then we can show that this is actually a vector space. Okay, so here we see that what vectors are not just tuples, right? So we see that here continuous functions, continuous real valued functions are vectors. Okay, so vectors are not just arrays, they are broader than that. Let's see one more example of vectors. Now, if you consider polynomials of any degree, what do we mean by a polynomial? So we are still considering K to be a field, and you define a set where you are finding, you pick a scalar plus a scalar times the variable x plus a scalar times x squared, quadratic, cubic, you go on and on to n power. For any natural, not any natural number, not just any natural number, for any non-negative integer with your coefficient coming from the field. Then if you take collection, so this means polynomials of any degree. So you could have degree 0 polynomials, that would be the field. Degree 1 would be linear, degree 2 would be quadratic, cubic, and so on. So that's a very big set. And you define addition. So we need to define a vector space. All we need is what? How is addition defined? We define addition of two polynomials to be this. Degree 0, so as a subscript, degree 0s add, degree 1 elements add, and so on up to degree n elements. And for scalar multiplication, the scalar multiplies each of the coefficients of your variables there. So that means that what polynomials are vectors. So note polynomials are vectors. Polynomials are vectors. Let's look at our final example. The previous one was polynomials of any degree, but if we restrict ourselves to polynomials of degree at most n. So if you pick any non-negative integer n, and look at the set of all polynomials with degree at most n, right? So at most n, that's why we put the subscript here. Then with the addition and scalar multiplication in the previous page, this also becomes a vector space. So here, so in summary, what have we seen? So here in summary, we've seen that what? Vectors are objects that we can what? So vectors are objects that we can add or scale. And add or scale. We've seen that what? Polynomials are vectors. We also saw that continuous real valued functions are vectors. Functions are vectors. Okay, so vectors are not just the tuples that we see. Even polynomials are vectors, matrices are vectors, and so on. Thank you so much for watching this definition of a vector space. Next, we go to other properties of vector spaces and other concepts. Thank you.